Okay, let's go ahead and get ourselves started for today.
6 hours.
Okay, today, as most of you know, is Halloween. It's kind of a funny holiday. It's devoted to rotting your teeth by giving you candies, which are hopefully very enjoyable, but of questionable health. But go ahead and take many and enjoy, because you should get used to our bad traditions here. Not as good as bagels, but.
There you go.
More, oh no, take several. No, please. Yeah, I got more candy than you want to know.
Here's a program where you can send your leftover candy from the night and you can get toothbrushes instead.
that would be probably a much better use. Yeah, exactly like that. Yes, that would be good. People used to give away apples and healthy things like that, but that fell out of favor. People just want candy. They want Reese's peanut butter cups and M&Ms. I have heard. Okay, let us get ourselves going for today. Hopefully you're going to have a good holiday and you're surviving all your midterms and kind of making it through the quarter okay. Today we are going to go ahead and continue with a couple different threads and actually introduce some new ones, some that I actually find really, really fun, so I hope you will too. We're going to keep on going with a notion of components and creating custom geometries, but today we're going to start really cool. We're going to start looking at smarter components. So not only ones that are customizable, but ones that actually respond smartly to things in the environment around them and actually, kind of reformulate themselves in ways that are really very kind of cool to make them more useful. We're also going to continue with the whole notion of thinking about materials and how we work with materials, how we create different materials and assign them to different elements, because that's really the basis of rendering. Okay, and we're going to start talking about visualization and how we take all these models that we've been looking at, in a fairly flat, kind of just shaded view, and how we make something that's really much more photorealistic that could be used for architectural presentations, or even just, kind of product design presentations, really giving people a much more realistic sense as opposed to this kind of very abstracted sense of the way we model it. So that's our big agenda for today. Let's go ahead and get ourselves started with the notion of just really these custom geometries and how we work with those. And again, what we're going to be looking at is just how we start creating smarter components. And here's where we're basically going to be going. Let me pop back here. And hang on. This is where we want to start. It's really the whole notion of parameters and the types of parameters we can go ahead and add to objects. We've been sort of creating all sorts of different forms, really applying a lot of distance and length parameters to things to resize them, and really focusing on more of that than anything. We also talked a little bit about the notion of applying materials parameters to objects and how we can give people the ability to change the materials so they can render them and use them as they need them in their models. Okay, we played around a little bit with the whole notion of a yes-no checkbox, being able to turn on and off different elements depending on whether we want to see them. Okay, today we're going to play around with the whole notion of formulas and how we can use formulas to relate things together and actually create smarter geometry. Okay, we did that. Let's talk about formulas. So formulas have this whole language to them that is very useful for doing a lot of different things. We can calculate things we need to know, we can go ahead and control to make sure that certain clearances are always maintained, or we can actually go through and have objects that are smart about adding pieces as necessary just based on the dimensions. So a lot of different cool things we can do. And there are all sorts of formulas we can define. It uses a very similar syntax to Microsoft Excel or almost any programming language. You can say that, the area is length times width, you can compute things like the volume. Or you can actually start doing things like computing the number of elements based on a relationship like the total length of something divided by some spacing you want to maintain. So a lot of kind of cool things you can go through and create. There's all sorts of functions available to help us with that. There's all the simple arithmetic ones that you're used to, adding, subtracting, dividing, things like that. But there's also all these trigonometric and logarithmic and exponential functions, a lot of other cool functions available too, just depending upon how deep you want to get into it. And there's also the ability to go ahead and put in different little if conditions. So if something is greater than 6 feet, show it this way. If not, show it some other way. Okay, we can go ahead and control that. Again, much like Excel. So what to do with a condition, what to do if it's if it isn't true, Okay, different sorts of comparisons you can put in there. You know, conditional statements that can be either numeric or can include yes/no parameters. A lot of flexibility in this. But I think the best way to illustrate the value of this is probably actually to show you a pretty smart component that's in Revit and how it uses it. Then we can think about how we can reverse engineer our way to something that does something similar. And to get started along those lines, how about this? If you go out to coursework and pull on down from coursework, see if I can pop that up for a second. We'll say coursework. Let me log myself in here. GL cuts. Is it coming? There it is. Let me go over to 120. Head yourself over to session 12. And in session 12, you will find not only the slides for today's session, but you'll find 12B, the Smart K-Joist component example. So if you can, go ahead and load that on up. And we'll take a look at just really how that thing's constructed. So I'll go back over to Revit, and I'll open that up. My Smart K-Joist component example, and let's just take a look at it. So here's the idea. It's a very simple little Revit model. It's really just two walls, okay, as well as something, a K-joist, very similar to a beam, but has the ability to go ahead and resize itself nicely. So how this is working, this is actually a structural framing element. And if we were going to go through and put a beam in here, and we could do that, I could say choose a beam, and I could, let's see if I can make this work. Let me place the beam up on level 2. Okay, there, oops. Hang on, that's not what I want to put in. I want to put in a regular beam. Beam, let me switch to a different type. Like just a wide flange. Here's the idea. The wide flange that we just put in there, the nice thing about it is it's just a sweep. If you can sort of think in terms of the terms that we've been using for the past couple sessions. It is a profile of an eye section that's just extruded along a certain length or swept along a certain length. And in terms of doing that, you can make nice like straight sweeps. You can also make curved sweeps if you want to. It's really just a sweep of some type of a profile that's going along a path. And the nice thing about sweeps is they can be any arbitrary length. That could be 5'2", it could be 5'2 1/4", 5'2 3/8". It doesn't really matter. It can be any arbitrary length that we want to make the path. This K-bar, on the other hand, is a little bit different. It's got to be a little smart about this because the funny thing about K-bars, or kind of most truss-like elements, is, well, you can't just make them any arbitrary length. There's actually a pattern to this. There are end pieces on either side that have a certain geometry to them. There are middle pieces, okay? And have to be, you can't have half of a middle piece. You need to have whole pieces in there, whole increments to make it all work. So how this thing gets generated is actually a little bit complicated in terms of really trying to think about, each of these is really made to be a very specific piece for the precise length that's in there. And then, just the precise length or the sizes of the bays is really dependent upon that length. So let's kind of show you how that works. So, for example, let me control or zoom out here a little bit. I got this guy here, and how many bays are in there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I got 12. I'm counting these basically little V-shaped elements that are coming up. If I resize that thing, okay, it's going to add more of them. And that's actually kind of interesting in terms of what's going on. Let me choose it. You can actually see a little bit of the information that it's using to define this in the properties dialog. You can see that there actually is, there's some overall length here of 43 feet that is being divided into 14 panels that are each 3 feet and some change big. So it's going through and doing some calculations and figuring out that if the panel array length is 43 feet, okay, that it could be 14 panels and they're going to be 3 feet long. And let me change that ever so slightly. I'll say, hey, let's drag that out just a little further. See what that one is. Okay. Okay, now there are 15 panels, giving us a total length of 45 foot 6, 3 foot 0, and 51 1/28. Now there's 16 panels, 2 foot 11 and 5/8 each. So it's actually being pretty smart about what it's doing. Yes?
So there's no length at which you stretch it, at which you can say you can't get exactly that number, or can that be an issue?
It could be. What it's actually doing is kind of the opposite. It's taking any arbitrary length and saying, okay, I want panels that are about this ratio to the height, and then breaking an even number of panels within there. And what it does is the panel length is actually the whole increments. And you see these end pieces that are a little bit odd looking? Okay, that's where the change is going. The remainders are going there, and it's sizing those to be the remainder of what it can go through and create. Okay? So let's think about how you'd actually go through and create something like that, because it's a pretty interesting part, but the general principle of basically taking a length, dividing it into whole increments, and doing something with a change, or the remainders, is actually a pretty useful one. So the way we'll explore this part and really use it as the basis for understanding our own part is just by opening it, and we can do this with really any Revit family. I'll choose that family and I'll say, hey, I got the family, it's hanging out there right now. I want to open it. I will edit the family. And it'll take you back into the family editor, the very same family editor that we've been using so far in terms of what we've been up to. And we'll see a little bit how that's defined. Okay, if I go to, of all the different views here, the elevation view, that's probably the most telling. Yeah, let me try the floor plan view too. I'm just gonna see if I can figure out where if the overall dimensions are there. There they are. So at a high level, as smart as this thing is, it really starts with the notion of there is a length. Zoom out, zoom out. Okay, and that length is divided up into 2 equal segments on the bottom, has those equality constraints. And that's pretty similar. We've been doing that with our own stuff. Green lines, overall length, kind of split it, make it even so that it always stays centered. In the front view, you'll see there's all sorts of interesting stuff going on the ends. We have some notion of a panel, where a panel is one of these individual V sections. Okay, it's equally spaced around some sort of center. And there's this notion of an end panel. And really the best thing to do is actually just look at how these parameters are defined by going to the family types and kind of checking out the formulas. So here's the way it basically works. Let's see if we can figure this out. Okay, there's something that's the overall length. That's the total length of everything. There's something that's going to be called the panel array length. Okay, and the panel array length, it's the total length minus 2 times what it's considering to be the end panel. There's some end panel, which is the odd part. So there's the part that's very, very regular. So it's doing this, and then kind of coming doing this. And then it's got that long piece. So what it's trying to figure out is if this is the total length right here, this part which is very regular, and I'll pardon my not looking very regular there, okay, this is what it's calling the panel array length. That's the part that's going to be incredibly systematic and repeated, and then this is the end. And that part over there is the end. So it's saying, okay, the panel array length is going to be the total length minus 2 of the ends. And the ends are going to be just 2 times the depth, so 2 times the height. So they're basically saying if this thing is like 18 inches, that this is going to be 2 times the depth. So it should be something like 36. Let's see if it is. No, we can't tell. So the end panel is 3 feet. Yeah, okay, it actually adds up. Okay, so the depth of this thing is 18, 1'6". The end panel is 3 feet. So we'll take the total length of whatever it is. This one was 24. We'll subtract off 6 feet, and we'll end up with 18 feet left over. Okay, so that's where that is. The panel array length is coming from. Okay, then we say, great. We have the panel array length. Okay, let's go ahead and talk about how many numbers we need to divide that into. Okay, so what they're doing is saying that any individual panel is 2 times the depth. We're taking the array length and dividing it by that. So, if this was 3 feet over here, and this was 3 feet over here, and this part over here, in this example, just the way the parameters right now is 18 feet. Okay, we're going to divide that by 2 times the end panel, or 3 feet. Right? Okay, and figure out the number that we're going to get. So it's going to be 18 divided by 3. 2 times the depth, yeah. Okay. 3 feet. It's going to give me 6 panels. So that means there's going to be 6 of those in there, kind of evenly spaced. Makes some sense? Okay. We'll go ahead and come up with an example that's somewhat similar to that, but maybe a little bit simpler. But it really is all driven by these formulas and setting things up. And using this kind of algorithm, you can really come up with things that'll do very nice things, arbitrarily sizing to almost any length, and kind of be very smart about spacing things out. Okay. And you have this sort of situation. If, for example, you're doing some sort of tall bookcase, okay, and you know that there are always going to be like 5 shelves or whatever it is in there, there's sort of this issue. Well, no, I take that back. There's a number of ways you can approach this. One is we can sort of split shelves evenly on the bookcase. So no matter what the height is, we want to have those sort of split up. We can say that, no, we actually want to be a little bit smart about this. We want to say that, we want to put as many shelves as will fit in there. The shelves have to be at least 12 inches tall. But if they get any higher than 18 inches, then I want to put another shelf in there. Or maximize the number of shelves such that each one's at least 12 inches tall. A rule like that, and you can sort of build it with formulas. The other one that I keep on using as an example is, because I think it's an easy one, this whole notion of a table, and then based upon the length of the table, we sort of just change the number of legs. Whether it's going to be 4 legs, or 6 legs, or 8 legs, or however many legs to tie it all together. And maybe we'll even do the other thing I was showing in the other class. We'll think about sort of this lazy Susan that's going to be in the middle of it. Some sort of turntable, and making that smartly sized too. So let's take a look at just sort of creating pieces that are smart. They have some sort of formulas behind them, and that'll be part of your repertoire, basically how you can go through and create elements. So if I was going to go through and create this table, okay, we'll start with, let's just kind of think about the different pieces that we're going to create. We're going to start by creating some like extrusion probably for the tabletop. Okay, it's going to have some sort of length and a width or depth. Okay, so I'll make some of these things, I'll make some of those, and basically control the dimensions of each of those things, directions. Okay, I'm then also going to go through and create some little extrusion which is going to sit on top of it. And for that one, I'm going to control its radius. Okay, so let's go ahead and see if we can do that part. Then we'll add the table legs and kind of make it smarter. Okay, so coming on back over here, let's cancel that. Hold on to this one. It's a good example. And we'll say new. I'm just going to give myself a new family as a starting point. And again, I'll just make it a furniture family for now. We have those typical front or left, right, and front, back center lines. I want to create the extrusion from the tabletop first, and to do that, just like we did last time. Hopefully this is looking sort of familiar, and I'll apologize if it's kind of getting boring. But this should hopefully be very familiar to you at this point, where I'm starting to just sort of put some reference lines down. Oops, that one's a little off. Let me square this one out for you. Okay, now, same basic procedure I always use. I'm going to put some line or dimensions on this. I'm going to put some dimensions on this one. Okay, I'm going to call that one the length. So adding a parameter to it. I'm going to add a parameter to this one and call it the depth. Okay, I always add those equality constraints, and again, the reason I do that is I just want to make sure that this thing is always balanced around the center points. So I'll add an equality here, and I'll add an equality on this side. Okay, and as I'm placing these, it doesn't matter where I place the dimensions. I can place them in any view. Those dimensions will dominate. Sometimes I put them to the left, sometimes I put them to the right. I just try to keep them out of the way of each other so you can sort of see them better. Okay, so far so good? Okay, you got that? Let's just create a little piece of form to put within there. Again, I'll do this thing where I won't go ahead and put it right on the lines, because what I like to do is actually align it to the lines and really make sure it locks in there tight. Oops, wrong way. Beautiful. Okay, in terms of the start and stop, I always have to remember this. I think tabletops, if my memory serves me, are right around 28 inches tall. Is that right? Is anyone else know? I think it's around 28. Yeah. There's all these other countertops are 36. Bathroom counters are 32. I'm pretty sure tabletops are 28. But I could be off on that. I'll say make that 2'4", and I'll make it like a 2-inch thick one, so 2'2". And again, we can add some parameters to control that in the other direction, but let's just kind of put it in there manually for now. Finish that up. I got my first piece. Hopefully I got a nice resizable tabletop now. Okay, in the same sense that I say I always like to go through and flex and test to make sure it works. Before I go any further, because it's going to make this a lot more complicated, let's just go ahead and change it and see if we think it's doing the right thing. Actually, I can resize that. That might just make it a little bit easier. By 2 feet. Beautiful. By 7 feet. Okay, looks like it's doing it. Okay. I could even start adding parameter or formulas in at this point. For example, I could create some relationship between the length and the depth. Maybe I'll do that. That's actually not a bad thing to do just to start with, just to kind of demonstrate this. So for example, if I knew that I always wanted to have a 2-to-1 relationship or a 3-to-1 relationship, whatever it is between the length and the depth, I could put a formula in there. So I could say that, you know, the length or the depth is always going to be length, let's say divided by 3. Just to give ourselves a 3-to-1 relationship. Apply that. And what's going to happen now is there's always going to be that relationship. So let's kind of think about how it works. So if I go through and put 9 in there, it computes 3. See if it works the other way. If I put 4 in here, well, it'll compute 12. So it's actually a two-way relationship. Okay, but there's basically a relationship between those two things. Okay, so far so good. Simple formula, just kind of tying those things. Let's go ahead and think about this little turntable guy, because he's kind of a good one too. How about for the turntable, let's go ahead and add another little piece of form in here. And for this one, I'm actually going to control the radius. Actually, I haven't shown you how to control a radius with a dimension, but it's really the same as controlling the length. Let's go over to the reference level, just so I can draw from the top. I want to draw an extrusion now, and let's see if I can make this work. Oops. Kind of a weird thing about circles, just so you know, circles don't have reference planes kind of in the same sense. You can't bound them the same way. It's a little odd, but we'll see if we can make this work. Let me do an extrusion, make it a circle. Now, I am again going to draw this a little off. I could try and put it just right in here, and if I'm lucky, and well, let me try to see if it does do it. I think it will do the smart thing and lock it to that point. I'm trying to basically lock the center line to the center of the table. And I think since I explicitly chose that, it'll pick that up implicitly as being a lock. If it doesn't, I can go back and sort of lock that in there. Let me see if it's going to do it. See if it can make it easy for you first. Okay, I got this little turntable here. Okay, it's got some sort of, let's put some dimensions on it. Of the different dimensions that we have here, one of the ones we haven't used very much is the radial dimension. It'll just put a radius on there. Okay, and in the same sense here, we can put a parameter on this. Let me call this the turntable radius. Okay, not too bad. And what kind of relationship do we want to set up for that thing? Okay. Theoretically, hopefully it'll never get to be more than depth divided by 2, or it's going to be hanging off the table. That's sort of one way to look at it, but we can sort of really put any kind of relationship. What kind of relationship would you like it to have relative to the table width or the length? Because we can define it either way. Any suggestions? Don't all jump in. Anyone at all? Yeah, you want to make it by 3, you want to make it by, we can just make almost anything in there. Let's say, how about, let me say that it's going to be the depth divided by, let's say 2.5. Again, anything over than 2, it's going to hang out. It won't care that it's hanging out, but anything over than 2, it'll try and hang out. Say okay to that. Finish that little piece of form up. We'll see how we're doing. Oops. Looks like it's actually sitting right on the tabletop right now. Let me put it up a little bit. I'm going to make it from 2 foot 4.5 up to 2 foot 6.5. Just want to give a little raise. Okay, so let's see if we can make this thing work. In the same sense now, we should be able to derive this almost any direction. Let's see what happens if we make it a 10-foot table. If we make it a 20-foot table. Okay, let's go ahead and make it an 8-foot table. So not too awfully bad. It's good. It's resizing. We can build this in a number of different ways. Okay, we could, for example, kind of complicate our life here a little bit. We could, for example, say that, okay, the turntable radius is going to be, divided by 2.5, but we could actually make that more of an if condition if we wanted to. So let's kind of take back a look over here. We could say if some condition, do something if true, something if false. Yes?
This is going back behind the formula to my own misses, but if there's a goal and I try to put mine and it says constraints are not satisfied.
Okay. That usually has something to do with there may be too many constraints, or there's something about it that it just doesn't think it can make the geometry. So something about the way your formula is defined and the parameters, it doesn't think it can physically make it. Let me see what you have. Let's see if we can figure it out.
Like you said.
Yeah. Well, that'll work. Let's see what's going on here. So length divided by 3. That should be fine. So what's the deal? When you say apply that, you get constraints are not satisfied? Say remove the constraints from it. And let's just see if we get the math to work. Change the length or something like that. We might, or actually just change what numbers. Okay, so it seems to be doing the math okay. But there's something, it may not be driving the geometry. It's weird. Say remove the constraints again. Let's go back to your picture. It might be, there's something that it thinks was just, I think it actually just took out a constraint right there. Something was concerning it. I'm not sure what it is. Don't know. We'd have to kind of look at it. There's something about the, it's just a little, it's a little confused right now is what it's up to. But when you get that constraints are not satisfied, if you can't figure out what it is, remove the constraint and see what drops out. Because when it removes the constraint, hopefully, you get kind of a good answer. So let's think about this. We can say that, like, we have one ratio. Let's say that, what do we want to do? maybe if the table was very small, no, let's just change the ratio. Let's do this. Let's say that if the table is very wide, we have a kind of a different proportion versus the turntable to the width depth of the table versus if the table is very narrow. So we have sort of two different ones. And the way we would implement something like that is we could say that if, and put a little if condition there, and if I'll say if depth, and we could put in there, oh, let's say if depth is greater than 3 feet, comma, let's do depth divided by 2.5. But if it's going to be less than 3 feet, the other side, we'll say it's going to be depth divided by 3. Let's see if that works. So what's happening now is the constraint's a little bit different. In this case, depth is less than 3. Okay, so the turntable radius is being computed as being depth divided by 2.5. Okay, coming up with this. Let's switch it over to being a much bigger depth. So I'll make this 12 feet. Now the depth is 4 feet. Okay, so now it should be depth of 4 divided by 2.5. Hang on. So that depth is greater than 3. Depth divided by 2.5, 4 feet. Oh, that's hard to tell. I need something that's going to be an even increment of 5. Depth is 5, depth divided by 2.5, 2 feet. Okay, yes, that's what we're doing it. So we're getting two different formulas just depending upon the width. So the proportionality is going to be a little different. But you go ahead and sort of, build that in, just really any sort of if formulas you want to kind of control that stuff. Okay, so let's leave it at that. Okay, so we got our table, it's kind of doing okay. Let's go ahead and put some legs on this thing. Okay, and putting the legs on there, I'm going to actually show you kind of an interesting way to do it. We could go ahead and just extrude the legs up. Okay, and that might be a way to do it. So I could come over here and go back to the reference level and say, super, I'm going to put some legs on this thing. Yes?
Before you do that, if the turntable is not attached to the center of the table, what are you supposed to do?
Ah, let's think about that. If it wasn't, what I would do is I'd go through and grab the little turntable. I would say edit its extrusion. See if I can pull it off for you. See if I can align this right. I'm going to use the align tool, and what I'm going to do is say align the center line here. And if I hover, can I get it? Is it not going to do it? It doesn't look like it's going to do it. Let me see if I can do it. I'll try another way to get this to work. Ba, 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 ba. I'm looking for my different things. I'm going to try adding something called a model line. No, I think that's going to bother me because it's going to try and do that. Let me try. I'm playing around here a little bit to figure out the best way to do this myself. Let me try adding a symbolic line. No, it's still not doing that. What I basically need to do is do an align on this. And there is a way to align a circle, but it's kind of a hard thing, and that's why I always sort of mess around with it. Now it's just moving the line down. It's going to make me think this morning, and that's a dangerous thing. I need to basically come up with a handle for it. What I want is actually just put like a detail line. Da, da, da. Let me finish this. See if I can do it outside of this. What I'm basically is trying to basically attach a piece of geometry. No, I'm just going to pull the line across. There's always a way to get to the center, and I'm just having trouble finding what it is now, because usually I can go and snap to it. Yes?
Can you just move use the move tool based
Oh.
on the size of the
That's actually not a bad thing. Let's see if, a very good suggestion. Let's see if it'll do that and give us the option to locking. Now, we're putting it there. Again, it didn't give me much of a lock. I'm trying to find a way to lock it. Zoom out, but you're sort of not too bad in terms of doing that. The question is if we can get it to sort of give us an implicit lock at that point. It's not there. I don't know. Let me figure out how it works in the latest version. For now, try moving it over there as suggested. See if I can come up with a better way to do that. I might actually, well, I'm going to think about a better way to do that as two separate pieces. Let me show you what I'm going to do in the next piece, and I think it'll work for doing this radius thing, or this turntable thing. Sometimes, as we're going through and building things, it actually makes sense to go through and build them in parts, separate parts, and bring them all together. And as part of the separate parts, you end up having reference planes that let you go through and kind of pull them together kind of the way you need to if you need to get them back online. So let me see if I can make that work. Yeah, I'll do it to the legs and I'll come back and show you. Remind me about the turntable. I'll show you how you make it work there. Okay, so here's the deal. I could go ahead and just start extruding. So I could come over here and I say, hey, I got my table. That's looking good. Let me make another extrusion. And I'm just going to start putting the legs in here. And that may work. I could also go through, actually, let's be smarter about it in terms of what's going on. If I want the legs to be moving around properly and kind of have the right relationship to the outside of the table and things like that, what I probably would want to do is go through and put in some reference planes. So I'll put a reference plane over here. I'll put a reference plane over here. I'm going to put some, just really, I'm trying to basically bound in the locations where I want to put the four legs. And now that I've put these in place, I can do some annotations, adding some dimensions. And again, I can put these in as parameters, or in this case, I'm not going to bother putting them in as parameters. I'm just going to put them in as like fixed locations. I'm going to shrink up the table a little bit so it's easier for me to see what's going on. So I'm going to put in some annotations. I'm going to say that from, oops, got it on the outside now. Annotate. We'll go through and make a dimension from here to here. Make a dimension from here to here. Now, again, if I put these dimensions in, I'm pretty good at guessing 4 inches. Jeez. Okay, that's enough for those. I don't need to put one on the bottom. Okay, let me zoom out. Do the same thing over on this side. That one doesn't look like 4 inches. So I'll choose it and make the 4 inches up here. Okay. My goal is to say, hey, yeah, are those lines going to move relative to the outside bounds of the table? After putting those on, let's try it out. Let's make it a 9-foot table. Okay, looks like they're hanging out at 4 inches. That's looking pretty good. So at this point, I can start actually doing some extrusions and kind of locking things to those. I can put some sort of table leg, something like that in there. So the extrusion could look like, let's go ahead and create an extrusion. I can make some sort of little table leg. Let's make it kind of a dumb little table leg. Ah, you'll see actually this time I actually drew it right in there. See if it'll even work with a move. I happen to draw it right in the place. No. Okay. What I'll do, same sort of aligning. I want to align this one to that one. I want to align this one to that one. Okay, still want to get that 4x4. Okay, I'm going to go through and make the other ones too. I'll say, okay, great, you're over here. Notice that actually this time, this is what I call like offering you the implicit locks. Okay, where it's basically saying, okay, I'm noticing that you're you're potentially locking to a lot of different things here, and it's offering some of those. So I could lock it down to here. I could either implicitly lock it or explicitly lock it, where I can choose that. It sort of seems to know that it's locked up to that one there, but again, align this to that. Align this to that. Okay, and I'll leave it at that for a second. Put those, oops. They're gonna go from 0 to 2'2". Okay, let's take a look at that. So hopefully, as I go moving this around, and I could have done the other 2 legs too. Yeah, we sort of repeated it. Let's take this thing, and I'm going to make it, now it's the 15-foot table. Okay, and hopefully the legs are moving with it and stuff like that. Now, you might have noticed something sort of inefficient about what I'm doing as I'm drawing all these different legs. Turns out, if the legs are really kind of the same leg in all the different locations, I don't necessarily want to extrude it 4 different times, or 6 different times, or 8 different times. I kind of like to be smarter. I'd like there to sort of be a leg object that I can insert into my table object. Okay, and that's actually a more powerful way of doing this, is to actually go through and, as opposed to just extruding everything, think about parts being built out of other parts and assemblies that are built out of smaller parts and how they all work together, because that actually gives you some power in terms of how you're doing this. If I want 4 different legs and all 4 of the legs essentially want to be the same, why not model it once and just insert it 4 times? Okay, could have all the same materials properties. The other nice thing about doing it that way is we can create arrays of those parts, and they'll stretch or do what we want to have them do properly. Okay, an array being a repeated number of them that are kind of spaced out at some even increment. Okay, so if you're arraying things, and I like to array things an awful lot to kind of make repeated ones, like this whole panel thing was arrayed. That's how it kind of came on down. If you do it as extrusions, extrusions don't necessarily array very nicely because they tend to lock to one side or they lock to another side. So when it gets arrayed on down, it often gets confused about how things show up. And the way this classically shows up, I'm just going to draw you the example. You can sort of see it is, I used to say, okay, great, we're going to go through and, make some wall. And I would go through and put some sort of framing in the wall. So I just arrayed, I'd extrude that up. Okay. And then I would go through and array it across. So I'd go ahead and have a bunch of them at 16 inches or something like that, kind of like the framing in a wall. And that's all kind of cool. But I do that by basically locking this to the bottom and locking it to the top. Then I'd say, okay, I can be smart about this. Let's go ahead and change that length there. So let's go ahead and make that taller. So it pops up here. You know, this thing grows. up to here. That part's all cool. Okay, so here's what would happen. And what it was doing, it's saying, great, I'll take this one and attach it to the bottom. Oh, and I'll take this one and I'll attach it to the top. And I'll evenly space everything out in between. But often when you're arraying an extrusion, it has a hard time understanding that you're trying to get both the top and the bottom constrained. So the better thing to do is actually to go through and put in an object that is explicitly constrained to the top and bottom and array that. It seems to be sort of a stronger way of doing it. So let me show you how you'd apply that to the table problem. And it's kind of a good general purpose thing. I'm going to advise whenever you want to array things, it's almost always better to go through and make a subbed object and bring it in. Can control it that way. Okay, so that sounds very highfalutin, but it's actually easier seen than actually probably explained. I'm going to say, let's create another family, my little furniture family. Okay, looks amazingly like the old one. I'm going to create an extrusion that'll be my leg. Maybe I'm just going to make a nice little round table leg. Again, not looking too bad. Let me finish that up. Go back to the elevation view. Okay. For my table leg, I'd like to be able to go ahead and have it have a controllable height. So what I'll do is I will put a reference plane in. Okay. And I'm actually going to go through and put in a dimension from here down to here. Oops. I will align. Okay. And this guy, I'll give a parameter, I'll call it table leg height. So nothing too awfully special there. This is really just kind of a single piece. Zoom out. Hopefully as I go through and change the table leg height to 2 feet or whatever, it'll stretch and behave nicely. Okay, so I just got a little table leg there. Does that feel pretty good? Hopefully that was pretty straightforward, just a single little piece like that. Let me go ahead and save this away. Okay, you would like to take that table leg and actually use it inside your table. So what I'm going to do is load it into, and I can insert it if I want to do that way. I'm going to pull it over into my little table family. Okay, and now I have it as a part available inside my table family. So kind of like I have families inside of projects, I could have families inside of families inside of families and kind of build things up from scratch that way. So the nice thing about it, here's my little table leg. It's kind of hanging out over here. He's not looking too awfully bad. I can take that little table leg and I can start using him inside my family. So I'll go back to that reference label or level, and I'll say, you know, these guys, they're just really not good news. Out of here. Instead, what I'm going to do is take my little table leg and bring him in. Now, the nice thing about the table leg is the table leg actually has these little reference planes built into it. Remember that left, right, center that we always have in there? They're available for the table leg here, even though you can't see it. So when I try to align, for example, the center line to the center line of the table leg, I actually have something that I can lock. And that's why when we got in trouble on the turntable, I'm suggesting the better way to do it is if we make the turntable as a separate piece, it picks up reference planes that then let us lock things into place. So let me come over here and I'll lock that in there. So what's going to happen now? That table leg in the center of that table leg, as long as we want it to be, is always going to be locked to that. Okay, and that's a really nice strong relationship. Now, you like that table leg? He's looking pretty good. let's go ahead and duplicate him. Okay, he's not locked. I just copied him over there, but let's make sure that one's locked in here place. So I'll lock it here to here, and I'll lock it here to there. Okay, those little reference planes are really good. I can always grab onto reference planes. Zoom on out. I need a couple down on the other side of the world too. I'm going to grab those two. So I only grabbed one. Now, we'll go this way. And I'll copy it up there. Again, I'm going to lock it in place in just a second here. I will align. You get to use the AL keys an awful lot. AL for align, and then kind of get out. Finally, we'll go over here. Oops, I think I blew that one. Align. Actually, I think I did that one twice, didn't I? I think I got it. We'll see in a second when I try moving it around. So hopefully I got my little 4 table legs there. Let's go ahead and change this table. It's a 20-foot table.
Glenn,
Yes?
what do you do since they're not like actually attached?
So again?
They're aligned, but the table legs are on a different plane than the actual table.
A very good question. How kind of you to notice that. 'Cause that's a really good question. Okay, we got these legs. They're moving around all fine, but you see that little gap in there. Okay, it's kind of hanging around. We actually want to have a relationship between the height of the table, okay, and the height of the legs, okay? And sounds like we might be able to use a parameter to kind of tie those things together. So here's how we do that. Okay, we are going to go through and basically in the front view, you'll see the problem really well. Right in there. We basically want to lock. We want to basically measure to the bottom of the table and then use that same measurement as the height of the legs. Kind of get those things all together. Does that make sense? Okay, let's zoom on out and see if we can do that. So what I'm going to do is I am going to take a little reference plane. If I can find it. Oh, let me do this. I'm going to make something called table height. I'm going to make something over here called table bottom. Okay. Let me go through and put a dimension in from the reference level up to the tabletop. I have sort of a choice here. I can decide, whether I want to measure to the top or the bottom. I tend to think about that in terms of the tabletop height. So this is going to be add a parameter, tabletop. Oops, spelled badly. Let me go through and add another parameter. I'm going to call that one table bottom. I'll fix that in just a second. Okay, I need to do a little aligning just to kind of make my life happy. I'll align the top of the table to that and align the bottom of the table to that. Okay, I'm actually going to put a relationship in between those because I always want, I can say I could put table thickness in there, but I want to have table bottom be like 2 inches less than tabletop or something like that for our example here. So I'll say, great, I have tabletop, I'm going to have table bottom be table. That's really bothering me up there. Ah, stop that. Don't laugh. Okay, table top. Okay, table bottom is going to be table top minus 2 inches. Okay, that'll get those things related. Okay, hopefully that's looking good. Okay, so far I got this tabletop. I should probably take my Lazy Susan and put it up on top of the table too, but we'll let that fly for right now. I would love to have a beautiful relationship between tabletop or table bottom and top of the table leg. Okay, and how can we do that? What's that?
Can you align it?
You wish you could. It's so close. Well, actually, that might actually even work. I'm going to drive it with a parameter. It might actually work that way. But here's what I'm going to do. I'm going to take these guys, and it turns out... Oh, I needed to go through and make it an instance parameter. Well, no, I take that back. No, I think it's a type parameter. Wait, let me do this one. Edit the type. It's got this parameter called table leg height. Okay, if we relate it, we can actually grab the table bottom, which we've just defined, okay, and link the two things together. So now, whatever happens to table bottom, that is going to be driven down into the leg, and the leg is going to be the appropriate size. So I'll say that, say that. Actually, that was probably even not a bad way to do it, because now they're all for the right height. Woo! Okay, we're doing pretty good. Except for that Lazy Susan hanging under the table, but we'll get that one fixed. Okay, let us do this. Let us go ahead and give our ever so brief pause for 5 minutes. Come grab some more candy, do whatever you need, and come on back in 5, and we will complete our exercise of basically saying, my fantastic legs, I want to kind of array them around and have a bunch of them.